actually is additive manufacturing? I know it's not a new term, but how the AI is working in additive manufacturing? What are the aspects involved in real-time monitoring for additive manufacturing? How the AI is helping the additive manufacturing process to get the decision informed and doing some process optimization there, right? So going to the first term, that Industry 4.0, like we all know this, like we term Industry 4.0 as the fourth industrial revolution, and we are just entering now industry 5. That's what actually currently the what do you say, the business ecosystem terms as. So when we talk about Industry 4.0, it's all about like intelligent networking of entire business ecosystem through some advanced information and communication technology. And what I would say, like digital twin is one of its core enabler. Okay, that's what what I tell you from like according to the ISO standards. So which connects its machine, or what we say operators, products, and product ecosystem with not only with the business but also with the environment and with the what do you say the different elements of the business. So when we talk about the business ecosystem, so it's like business model, its environment, or we talk about its production system, then it could be like the machines, operator, product, or what do you say as the services there. So when we look at the Industry 4.0 basics, so it is understood to be like the three different dimensions. So the first dimension is about its development. So we divide the first dimension into two, like type and instances. So type is like development and management usage, and in the product in the instance it's like production and the maintenance usage. So when we talk about like the development, so it's like designing of an idea, and maintenance usage like maintaining of assets used for the development purpose. And when it comes to production, it's like manufacturing of the ideas that's been already designed in the previous stage. And once we have like we use once we use some asset for manufacturing, then maintenance usage is like maintaining that particular assets at the level of a digital technology. The third dimension is the Industry 3.0 model. So we each industry model, as industry model like 1.0 or 2.0, is built on its previous industry model. Like for an Industry 4.0 model is going to build on the Industry 3.0 model. So that's the second dimension of the model. So Industry 3.0, it's just focused on the assets. Assets in the sense, for example, the physical assets, machine. Then there could be like devices, products. Okay, then the third dimension comes of in Industry 4.0 is as a digitalization, making the particular integration of different layers in the business ecosystem. Okay, so in the first layer of the third dimension is assets. So assets can be like a physical assets, or it can be like a non-physical assets. Then it could be like the integration. Second layer is integration. Integration is like we want to digitalize this information that is coming out from the assets. In digitalizing means like it could be like real-time monitoring, or making use of like QR codes to digitalize or get the real-time information, or imposing some sort of like accurate technology to identify the lifespan of the machines, etc. Then the third layer of the what is the third dimension is the communication. So we have the assets, we are integrating with some sort of like sensors, but it's also important that we need to communicate that whatever information is being given from getting from the assets. Communication is like industrial IoT. That's what we use, like whether it could be like a wireless communication or through different way of communication there. So communication is just the communication of information from assets, and by integrating those assets with the different layers there. The third is the D, is all that third layer. D is layer is on information. So extracting useful information. So that is like data analytics. So if you just remember of yesterday's lecture of smart manufacturing, there are 4 different pillars: IoT, data analytics, cybersecurity, and one was like automation. Right. So this four different pillars of the smart manufacturing there, and that data analytics was one of those. So is one of uh, one of the particular aspect in the industry 4.0. So that's the D layer, that's fourth layer in the basics of industry 4. Sorry. Then the layer layer E is the functional layer. So based on the information, so functions of assets are identified. So once is again like is in terms of loop. So once you identify useful information, some informed decision, then or like for example optimize back to the assets, and you make the particular assets work according to the information that you have gotten. So that's like the layer E, that is functional. And oh my gosh. And then sorry, the layer F is the so business is that's last layer. So all of this has been integrated in all of the particular layers are integrated in the what do you say, in performing the optimized or a good business model there. So these are the different layers in the third dimension of industry 4.0. So we talk about digitalization. So that's like all the technologies or anything that's assets are that are specified in layer A. That could be physical assets and that could be non-physical assets as well. So industry 4.0 play a very key role in digitalizing these assets. But what are those technologies that are being used to digitalize this particular asset? So again, what I said was like IoT, cloud computing, the big data. Then there are robots, the simulation, then augmented reality, then the horizontal and vertical integration, system integration, additive manufacturing. Obviously, it's going to be one of the important assets in digitalizing the process, and the cyber physical system. So one of those industry 4.0 technology is cyber physical system. There is very authentic difference between the cyber physical system and digital twin. So I'm going to tell that once we go ahead in the particular presentation there. So first we'll look at role of every technologies that are associated with industry 4.0. So when we talk about industrial IoT, as again, this is the technology that enables the communication, the wireless communication between the physical assets, and we can say like for example the devices or locations. Okay, so that's like we call it of IoT. So making we are fixing off the like the internet devices or wireless devices that are the physical assets there. So one of the example is like making use of this IoT device in logistics. So in yesterday, one of the example I showed about the robots there, the two communicate by making use of the IoT. So one of this example could be in logistics. So that helps in managing the supply chain, where the product is where the truck is delivering the products, and we can trace the particular location of the product. What's the particular product, especially when the products are very fragile or like the products are has very really lower shelf life in food industries. So like for that case where the transporting is very has to be done very quickly. So in that case uh, IoT help us to understand very real-time information of its logistic information. So in IoT, it includes like the vehicle sensor, so it can track the location of the vehicle. The black box helps to understand the what is the information, background information, what condition the particular vehicle travel in, what was it like or like what is like harsh environment. So that type. In the package score, the package score is like that in case the product is having a lower shelf life. In that case, and the package score, like the smart packagings are coming up. So if you find in on the internet, there is smart is coming, a smart packaging system is coming. It was like, for example, they are fixing the that the packaging sensors on the package itself, so it track the real time. What do you say? It's productivity, or we can say it's like life of the particular product. Okay. This is what packaging is coming in. Then there could be logistics sensors and also the product sensor there. The other role of in the industry 4.0 is the cloud computing and big data. So cloud computing obviously is very important because we are not we are generating data at not like it's very huge data. So storage is another important parameter, and we can't just store that thing locally, because our information, if you want to make things smarter, that information has to be accessed by the operators in worldwide, right? So cloud computing is very important in that case, and where the big data is helpful in extracting the useful information out of it. Then the another role is in autonomous robots. Autonomous robots, as I told us about, like the robot which was used in performing. If you remember the case study yesterday I took, in the case study, robot was used to perform the machining task. Machine, it can pick the product from the machine, it can clean the product, it can store the or it can pack the product also. Okay, so that's enabling technology for autonomous robots. Then simulation is one of the most crucial aspects in the, what do you say, advanced manufacturing, or where the industry 4.0 is used. So computer simulation, which helps us to understand uh, better analysis and its dynamic analysis of the product and the process life cycle in the business ecosystem. Like it helps you right from designing to manufacturing and to transportation. So this is like all that before have opportunity to improve or optimize the process to just to increase the profitability. Next is the role of augmented reality. So this is one of the evolving technology. Most of the industries currently they use augmented reality. Augmented reality is like you just impose your what do you say, uh, the digital content on the physical world. Like for example, if you look at this machines here, so I can see there are the physical machines, but now if I want to understand its lifespan, sorry, if I want to understand its lifespan means, like for example, how much machine is operated or when the machine is under can be maintained. So for example, I can look at the score. Okay, based on the score, I can able to decide, okay, this particular machine is now has to go under maintenance, or this machine has still more lifespan and it can go for much more product. Okay, so this is like we can, through augmented reality, we can superimpose our digital content on the physical world or physical assets, I would say, and help to understand its productivity. The next is Industry 4.0 is the horizontal and vertical integration within within the system. So like horizontal integration is like when we talk about the intercompany integration, while the vertical integration is about the intra-company integration. So for example, intercompany means like there are different departments within the industry, so integrating those department, while in vertical integration is like intra, like in each department there are different levels, so integrating of those levels as one of the part of the or role of the industry 4.0. And obviously this is not going to be new for you, like role of additive manufacturing and advanced manufacturing. It's very common nowadays. But just to give a small information about what actually is. So we know that manufacturing of additive manufacturing process, where the CAD data is being used to manufacture the product layer by layer, and we use the term additive manufacturing based on the standards, ISO standards given. Uh, Also, like it's called as 3D printing, but now additive manufacturing is like common term that's being used by the standard there. The next is the cyber physical system. So cyber physical system we call the CPS as well. So cyber physical system is like we make use of a computer system in which the mechanism is monitored and controlled by the, what do you say, the computer based algorithms. So in the cyber physical system, so one layer is a physical layer. Physical layer is that has machines, okay, and that particular machines are continuously monitored by or monitored by some sort of like sensors. Like for example, if you can see on the screen here, the robots are being monitored by the vision cameras. So this vision camera, they continuously monitor the position of of the robot there, and then based on its current position or any kind of its system, the camera will send a real time information to the cyber layer there. So cyber layer is another layer which helps you to look at the position of the what do you say of the robot there, which is another like a device which continuously keep on monitoring that thing. And based on the position, like for example, if any controlling command has to be sent to the physical layer, then the cyber layer will send the physical information to the what is the physical layer, and accordingly controlling system will go in. There is actually a very thin line between the digital twin and cyber CPS. I told before, but I tell you about once you come understand the CPS now, and then I will tell about what actually digital twin, and then what's the difference between digital twin and the CPS. I'll tell you as we go ahead. The next we are going to look on is the digital twin. So digital twin, from the word itself, we can see like there is some twin elements which needs to be digitalized, right? So this digital twin is like very old concept. It's not like a new one. It's new in the field of manufacturing, but it was introduced by the the NASA, and it was first used for their Apollo space program. So it was like they want to go beyond the simulation. Simulation will give you the what do you say? It's physical appearance. It's what you say digital appearance of the particular model. But when it comes to real time simulation, that is where the simulation was lacking. So they decided to, like for example, break the barriers of simulators and like go beyond, so that if they can use the simulation for real time. Okay, so obviously they are doing, but we are still facing challenges in making simulation real time. Yesterday we had a chat on this, like how can we do the simulation, or what how can we do a simulation in real time. So currently, like they are making use of the physics and the generative AI together to make the simulations in real time, work in real time there, right? So that's what actually digital twin is. So when we talk about digital twin, so and simulator, so it's not about just it's digital model. Okay, so digital model is like, for example, let's say we prepare a CAD model of any product or any machine there. So that's the digital model. It just look alike of the physical model, but it will not share any kind of its physical information in real time. Okay, or it operational information. Like for example, if you make let's say if you design a CAD model of a lathe machine, and you have physical lathe machine in your workshop there, it can just look alike, but when it comes to sharing information between the physical and digital object, so that's not possible. So usually that is categorized as digital model. So it's just a look-alike model of your physical world, but does not have any interconnection. Then comes a digital shadow. Digital shadow is also called as a partial digital twin. The partial digital twin is like means, or digital shadow means, it helps you share information in one way. Like for example, a physical object can just share its real-time monitoring system to digital object. Okay, so there is a digital model, and it can share its physical presence. Or for example, let's say the robot. Okay, like for example, if I'm operating robot in its cell, and there is a digital model of the robot, so robot will send its physical information or physical presence of or its operation or the digital model, and accordingly digital model will be adjusted. Okay, like for example, we let's consider example of a what do you say a pick and place robot. So like for example, if robot is picking some object and placing it at another location, so the same thing will be the physical things will be shared by the to the digital object or digital model, and digital model will also behave according to like that. Okay, so it's like behavior of the digital model and physical model in the same way, but it will not send any controlling messages back to the physical. Like for example, if it's doing any pick and place task in a wrong way, and if I want to send any kind of controlling message back to the physical object, so that will not be sent. So this is like one direction information. That's called digital shadow. But that's like because I call it partial digital twin. And the next is the digital twin. So another added element in the digital twin for or added element in the digital shadow is the bidirectional information. So any controlling messages, some message will go back to the physical world, and accordingly the process will be adjusted. Obviously when I talk this, it looks very fascinating, but when we do it in an actual case, it's not that easy, not that easy task. But the very first difficulty you face in is building a digital object that will take the information from digital from the physical space. So that is very very challenging. So many of them are working this field itself. How can we build a digital object so that can take the real time information of physical objects. And then some other researchers are also focusing on how can we build on what do you say how can we send back that information to the physical object so that we can control that. And the digital twin, again, as I said before, it's an enhancer technology, so it's not been standardized. So there are a lot of definitions. So many of the researchers say that they can monitor the objects in real time, but the feedback or any information going back to the physical space, that can be or cannot be in real time. Okay, like for example, in case of there was a recent project or recent I think a talk I listened one on the digital twin for building environment space or maintaining the forest. Okay, so what is like they were tracking the health of the particular forest in real time. Okay, but in case of sending back to, like, if you want to send some like controlling measures, or like for example if they want to protect the forest, and if you want to send some controlling measures to protect that particular forest, that can be like after 1 day or 2 days or some after some time, not in real time. So they call this hospital also as the digital twin. So unless and until we get some standardized definition or standardized this thing on the digital twin, it's very hard to commit what is the standard definition of digital twin. So it's according to the research are twinning according to their particular research. But one common element in digital twin is like the bidirectional information. It should be so it's not only one way. It should go back to the physical world. So that is where the common element is there. So when we talk about a digital twin, so it's like a up-to-date representation of the actual physical assets in operation. So it can be a representation of the operation and its actual way, or it can be also in term of a digital way. Now, many of these particular aspects come into the CPS, cyber physical system. So in cyber physical system, we don't prepare any digital model there. So like for example, let's say if I go back to my presentation there. So if I look at this particular cyber layer here, so when we get this information, it will not represent this robot or any kind in the digital way in the computer. Okay, it will just show in the graphical way. Like for example, it will show the location in the graphs, like it can be like a 2D graph or 3D graph. It will not show the each and every physical or physical assets or a digital object of the physical assets there. So that is what the main difference between the cyber physical system and digital twin. Okay, cyber physical system, we can just look through a graphical way. Like for example, I monitor a temperature in real time. So I can have like x-axis to be time and y-axis to be like temperature. Okay, so time against temperature. So it can help me to understand how the temperature is behaving with respect to time. So that's like a graph in CPS. But when it comes to digital twin, you should have a digital version of its how is the temperature behaving, how is the temperature distribution taking place within the physical object in the real world that way. So that's what the digital twin is more about. So when we want to make use of the digital twin, so digital twin are like powerful because they support a wide range of application. So many of this particular application was the anomaly detection, so the detection of the defects, predictive maintenance. We call it as like asset performance or any kind of a management activities. So that is where the digital twin seems to be very powerful there. So depending on the applications need, the digital twin is operating at different level of the system, and we call that particular system to be like a smart asset. And at the age of real-time decision, that it could be like the IT infrastructure, which develops the large-scale data and helps to get the information out of it and optimize the physical assets in real time. So it's like, again, as I said before, some of the thing optimization uh, can be done in real time, but in some cases it may not be possible to do in real time. So there is a lot of confusion in the digital twin definition there. So here's one of the example here. How does the digital twin work? So like, for example, a digital twin of a pump is created by continuously updating a model with real-time data from the sensor and its operating conditions. So this actually allows the model to make a mirror image of the pump and its actual state. And the pump is the essential sensor that is from the pump will send information to the digital model. Your digital model will get updated, and accordingly it will help to understand the current state of the pump. And based on, now for example, again, it's like, as I said before, digital twin can be used in predictive maintenance. Predictive maintenance is, it can help to understand when we can go for predictive or maintain the pump there. Okay, so again, maintenance is not like a daily, right? It is done at some point. Your pump is giving real-time information to the model, a 3D model there. A 3D model is getting updated, and at some point, a digital twin will reflect that, okay, you need a maintenance like tomorrow or day after tomorrow. So your maintenance can be done, or you, what do you say, any kind of activity on the back to the physical assets can be done after some time. So this is where the two things are coming in. So feedback can be in real time and cannot be in real time. So this is the two different aspects that are involved in digital twin. So when we think about what actually is a digital twin, so there are certain ways where we think of building a digital twin or creating a digital twin. The very first thing is defining an object. So if you know the physical assets, so what is a particular assets working in, what type of environment, and what is that particular object is. So all that has to be identified, and first you need to define the object. The next thing is the identify the physical assets and system. So like, it could be real equipment, process, product. Like for example, in additive manufacturing, it could be like the additive manufacturing process itself, or it could be robotic arm, or it could be like a water pipeline, or it could be a turbine. So that's where actually in so then data acquisition. So IoT is coming in. So IoT is the one that helps you to capture the data. So capture data in wireless come away. So even though its location is far away from your original location, you can capture the data of your physical assets there. So, and there could be like mounting device like cameras, sensors like thermocouples for temperature, etc. Then there are data transmission. So that's like, again, for communication between the IoT sensors and the one your location there. So through the, so like 5G communication or like Wi-Fi communication. And then data processing and integration. So once we have the data in place, so if you remember yesterday, I told we are not getting data in small amount, we're getting data in huge amount, but it's not necessary that your data is clean every time. So when we come like data hygiene, so that's very important thing we need to have. Whether is your data hygiene enough to give the information? If not, then you have to go for cleaning, removing unnecessary information, unnecessary data, and making the particular data set clean. And again, you have to follow off a processing background, pre-processing steps for doing that, and then integrating that with the physical, what you say, digital twin there. Then there's a virtual model. That's what actually twin. So that's the difference between the CPS and the digital twin is. So we need to build a virtual model. This is the very, very, very big challenge in the digital twin, because as I said before, I can build a virtual model in the CAD. We have SolidWorks and all those things, but I can't operate that virtual model based on the sensor data, right? As I said before, your virtual model should also behave according to the physical model, the physical asset there. And CAD is not the option there. There are many other softwares are doing that, but it's not possible to do that, because in that, to send a real-time information from the physical to the virtual thing or virtual model that you have built in a software, you require a specific method. That specific method in the sense is like operational methods. right? So that has to be done there. So this is where the high demand is, building of virtual model of a physical assets. There are some commercial software, like you may across the term called Unity. So Unity is one of the software. There are other, but Unity is being widely used. It has the capability of building the virtual models, but again, they have their own way, like standard models, like they can go for modeling for robots, or even 3D printers can be done. Virtual model of 3D printing can be done in Unity. But if it comes to, like, for example, I have some in-house bespoke machine in my lab, then that particular software is quite like difficult, or it's very challenging to build that thing in that software. So again, we need to have some own methodology to build this virtual models. So once we have virtual model, then that could be like a visualization and control. Visualization is the its current real state of the physical assets, and controlling is the feedback control, which helps you to control which in of the particular process in and with or without real time aspect. So this is one of the digital twin virtual model of a BMW factory here. So they decided they built a particular virtual model based on their assembly line. So they have the car assembly line in Germany, and they want to digitalize this, or look at this particular every aspect of the digital components of the factory through digital way. So I'm just going to play a small video. This is a small video that help you to understand what does the virtual model mean. So what actually is the thing means in. So there is a different sensor that feeds information of the machine, man, robots. Okay, so and the production lines, and then they can build some virtual models based on their physical what do you say assets in their assembly line there. Right. So again, as I said before, now this is a big company, so that is the reason they were able to do this. But when it comes to like a small or medium, it's very difficult for them to implement this type of technologies. Um, Maybe in future I'm not saying it's impossible. It's possible, but technology will need to be more mature so that it can be implemented in small and medium scale industries. There is a large scope in this particular thing. So in summary, what I can say is like, how does the ecosystem of digital twin for advanced manufacturing with the help of industry 4.0 act is like, okay, so industry 4.0 help in capturing the digital assets of the physical assets there. And digital twin can be help to virtually build the replica of the business ecosystem, and not only the replica of the machines there, but it can help to build the replica of the world, the factory elements, and the products that they are building there. And this can help the communication between all the participants within the business ecosystem. And product is also the part of that network. So digital twin can also be like helpful in the life cycle management. So that is what the most important thing is. The next is I want to take you through like artificial intelligence additive manufacturing. So I know, I mean, it's a bit like difficult, like it's suddenly from digital twin to like artificial intelligence. This particular information, like I'm going to have some small case study on how the digital twin for additive manufacturing is built in. And but before that, I wanted to give some information about like what is actually monitoring, what actually is monitored in additive manufacturing, and how the decisions are being made. Thing and additive manufacturing. So the next step is the AI in additive manufacturing there. So I'm going to skip this step because this is everyone is known as what actually is additive manufacturing. So it's obviously building a product layer by layer. So when it comes to real-time process monitoring, so the first step if I divide the digital twin into three parts, the first step is you have to go for a monitoring of a physical assets. So physical assets, we need some sort of like a mechanism that can monitor the deposition process in additive manufacturing. Not only the deposition process, but also the what do you say, the behavior of the process during the project. For example, if I'm in a robot, then how the robot arm will be moving on. So that also like has to be done. So first thing comes in the real-time monitoring. So once you have real-time monitoring, next step will be you can integrate that data into the what do you say, the physical or virtual, to build a virtual model, and you can integrate that data into the virtual model to behave your virtual model same like that as the physical asset there. So while for capturing a data, especially in additive manufacturing, there are different sensors available: acoustic sensor, thermal sensor, or optical sensor, which being used to capture the data. And this data is being stored at certain location by making use of the cloud computing, and we make use of the machine learning to get its informed decision, right? And then also there are certain processes which can be done for in real-time controlling. So real-time controlling is possible now in additive manufacturing. So as I said before, if we build a digital twin for additive manufacturing, we can get real-time information in, and also real-time information to control the particular physical assets there. But when it comes to uh, monitoring, the sensors play a very important role. Again, if sensors are going to come in, then we need to understand their level of readiness. Okay, it's not as I said yesterday also, like it's not possible that every sensor is doing every job. There is some sensor or some job, but there are some aspects where the sensors are not available, still not available for doing that job. So in that case, we need to rely on other technology there. So like for example, if you look at the sensor technology, the optical imaging, thermal imaging, it's quite widely used, or thermocouples are widely used. So they are really high level where they're really available to use in the processes there. But when it comes to like X-rays or neutron diffraction, so this is one of the recently growing demand. So what happens, like usually when we have to monitor the deposition process, we have a cameras to do it from the top, okay, outer surface. But how could I know what's happening inside, okay, within the material? So like for example, if I'm depositing material and there could be a porosity inside, there could be a defect inside, the camera can give me outer aspect, but when it comes to inner aspect, they are very difficult. So nowadays the research is going on, I mean, using making a X-ray synchrotron, where they are passing the X-rays through the objects and helping you to get the internal structure of the deposition in real time. So when I'm X-rays are being used, not being now, it's being used for decades, but doing it in real time is the new thing nowadays, that is being used for real time process monitoring. So when it comes to like in situ monitoring techniques, so there are different we can divide different aspects here. So like for example, in case of, as I said before, uh, anything that can be detected at very high rate, lack of fusions, patterns, geometry defect, that is external defects, can be detected at a very high level. But because of we have a lot of sensors available for this purpose, but when it comes to like porosity, or that keyhole, or internal structures, or then delamination, it has medium detectability. Medium in the sense, like for example, the that X-ray synchrotron process, which is being used for detecting the defects within the component, that has a medium detectability. And when you go for very low chance, there is no availability of a real-time in situ monitoring, that's like its microstructure, chemical composition, we don't have this in real time. We obviously go after post deposition, or any kind of contaminations, or any kind of subsurface defects there. So this is one of the video that we captured on a powder bed deposition process. Not powder bed, it's a powder laser DD process. So where we make use of thermal cameras, and use of like microphones to understand its current state, based on its, like for example, let's say, um based on its current state, like what's its melt pull is, okay, how the behavior of the melt pull is going to be all to it in the real time. So this was done, and this particular thing. I think I'm running in time. I'm going to quickly think. So this is the glimpse of what actually is real time process monitoring can be done there. So next is like how to go with the decision informed manufacturing. So obviously decision informed manufacturing means defect is the most important part. So defects can be different defects, internal defects, or that could be like a void, flash formation, the keyholes, the pores, the gas. Okay, so we make use of the AI-based technologies for do that particular thing. So this is one of our research recently. We did it with one of the collaboration in India, that's IIT Indore. So they have the process called as microplasma transfer the manufacturing process, and we've been using some sort of like vision-based cameras to capture. So this particular our research was to capture the deposition process. Okay, so like for example, if you look at the bottom, there are two frames running. The left one is showing it clearly shows that the balling defects as we go on, while the another is like the continuous step out defects. And this study was also, we use this study to capture the spatter. So if you look at the small spatter particle, these two are very dangerous. So dangerous in the sense, like for example, these two, the spark going out, those are called as melted spatter particles, and these melted spatter particles, they usually get stuck to the deposition in the previous deposition, and that then damages the layer there. So that's where the thing is, or any melted spatter particles that go away, that get evaporated, that generates some sort of like gas there. Okay, some dangerous gas. So that's where one of the making use of the vision system to collect or monitor the spatter particles. Another aspect was to assess the deposition quality. So in the previous thing, we can, through eyes we can say, yeah, this is a bad deposition, or it's not a good quality, or boiling defects. But in the case of like the other one is showing the good deposition, with the eyes we can show, with our own intelligence we can say it's a good and bad. But what about how can the machine understand it? So we make use of the machine learning algorithms to make it, and we train it based on that. We help him to understand, okay, what's the good deposition, what's the bad deposition, and accordingly we can make that deposition quality information based on that. And it was not just like about understanding this. So it was like deployment in the real world is like we developed some sort of like mobile app, a camera based mobile app. So for example, you can just open that app and focus on the screen, where like for example, let's say there is a monitoring screen monitoring process going on, and you can just use the mobile app. You can just click and you can just focus on your mobile on the screen there. And so based on that, that particular application will tell you, okay, what's the deposition process going on there, so whether it's a good or bad deposition thing. So that was like some small project we recently did it. uh there's going just quickly go through the different optimization thing as well. So for possible parameter optimization, it's like for example, we can make use of the, what do you say, the optimization techniques. Okay, like most widely used, or I won't say like new, it's a very old one. We make use of the genetic algorithm based optimization process, where we try to build the objective functions for the, what do you say, the single tracks or multi-track depositions for predicting the width and height of the deposition. And based on that, we go on for genetic algorithm based optimization techniques for optimizing the process parameter and sending that information back to the machine for optimizing the process there. Yeah, so Anas, just I'll take you through the case study of digital twin for and additive manufacturing process there. So that is being used to monitor the robot position and also detect the defects in it. So the just a summary of the case study here. So in this case study, like we look at how the digital twin architecture for wire additive manufacturing is built. So like in this particular case study, like it includes the three-dimensional visualization of robotic cell or robot there, then the computer vision for part parameter detection, and then the CNN models for defect detections there, and the vision transformer for real-time anomaly detection or defect detection. And then by making use of the cloud-based data exchange like via Azure Blob Storage. So if you look at this architecture, so this is I'll just like to walk you through this particular architecture of the digital twin for WAM. So this proper architecture for WAM digital twin that integrates the physical system, there is a middleware and the digital system to achieve the real-time monitoring and controlling of the optimization process in an WAM process there. So in the physical entity layer, a robotic WAM setup equipped with like sensor and a data acquisition unit. So the data acquisition unit can be like the vision sensors, like camera, or it can be like thermocouple, so air camera, etc. So this will help you to collect the raw data, including like that could be like our characteristics or thermal profile or with different images. This data like support monitoring and allow parameter adjustment to control the deposition quality. The middleware is that helps you to bridge the what is the physical entity and your virtual entity there. So the middle layer is it has a lot of the things going in middle layer. So in the middle layer there is a cloud computing, there is a machine learning, there is like the blockchain where this particular aspects are being involved there. So in the middle layer is usually the bridge the physical and the digital system. So it makes use of the server or the client to enable like secure communication. The middle layer, it could be like a structured and unstructured data coming from the physical entity. The middle layer has to manage this type of information, whether the data is structured or unstructured, and it has to be, like for example, it has to be given in the proper way. So all this information is stored in the cloud computing and the big data that is stored, and then a strong security framework has to be included. So as I said before, when we are talking about data storage, and it could be like wherever there is internet or Wi-Fi, there's high possibility there is a security threat for that particular thing. So we need to ensure that our data is properly encrypted and it has proper certification storage there, and only certified persons or only security people can able to access those data. Okay, so that has to be there included in the middleware. And the final is the digital twin. So digital twin, as I said before, is the replica of the your physical entity. So like it's here the replica of the robot cell is being built here. Okay, so this is the 3D model that is being built by making use of. So this particular 3D model was built in the Unity software there, and then based on that the 3D model based on the physical entity and an information sent by the middleware, the robots will be determined by its current position, and the camera will help to also detect the defects in it. So if you look at the part one of the case study, so part one of the case study is the position of the robot arm. Okay, so what is the position of the robot's arm? So if you look at the joints of the robot's arm, so how can we monitor its physical or real-time position of the robot arm and replicate that position in the in the digital twin or digital model? So we make use the AI echo detection technique. So if you look at this black and white sticker here, so those are not actually codes, QR code, but those stickers we call it as like ARU code detection. So this is one of the method of that helps you to understand the rotation angle of the robot arm or the robot joint there. So there are different cameras that focuses on the sticker that helps you to capture the position there. And once we have this capture, then data is sent back to for handling, and this data in the cloud storage by making use of the Azure Blob. And then the storage helps us to analyze the current, what do you say, the current position of the robot. And then we already have digital model in the Unity software that software will take information of this robot angle in real time and it will move accordingly. So there is a small video here I would like to just play you through. So if you look on in the here, so like there's a physical asset in the left corner, no? Okay, so at if you look on, so as it moves on, there is movement in the angle there. So AR UCO detection codes stickers, they capture this rotation angles, and this angle rotation is being sent to the Unity software, and that helps to move the digital model according to the physical asset there. So this is just about what do you say, uh, capturing the location, okay, real time location of your robots there. The next was the anomaly detection. Anomaly means the defect detection. So again, we made use of like the vision sensors, and this data that we got captured from the vision sensor was sent to the different CNN models. CNN models like Swin Transformer or ConvexNet or AlexNet. Obviously, there are large is coming up, and data like there's YOLO, or you have like zero shot learning type of models where you can capture the time defects there. But this is some of the old study there, so where we can capture the defects, and we can integrate that with your what do you say, with the software as well. Like for example, if I'm trying to run that video for how the animals are detected. So if you look at video here, uh, in the inset, so that's like the vision based camera that captures the deposition process throughout its length. And if you look at the small thing, the green and red thing happening at the left, so right bottom corner, so helps you to under it's a bad status, like what is the status, is normal, is abnormal, means that there could be a defect there. Okay, so this is where the it helps you track the current status of the deposition process in real time. So in the conclusion of the case study, what I can say, like obviously some interesting findings can be seen, and some interesting thing can be done with the digital twin framework, especially in the field of additive manufacturing, where the visions can be sensors can be used to capture the real-time position, and the cloud computing can be used to handle the data, and the Unity software can be used to this thing. The main strength is that you can real-time monitor the physical assets and also control those physical assets there. And but the limitation is like you need to rely completely on the cloud storage like Azure Blob. Again, it's not that very easy, cheaper to get in, where the small or medium scale industries can work or afford this particular thing. So this has like very limitation there. And as I said before, there's different future work that is possible in this case studies, or that is like the control loop, like sending back the controlling loop in, like you can see, according to the bed, there is a bad defects going on. So according to, you can control what is the robot arm there, right? For example, if you want to maintain the robot speed or feed speed or traverse speed, so you can send that instruction back to the machine physical world, so that it can uh, uh, remove that particular eliminate of the references that I have used for preparing this presentation. Thank you very much for time. Apologies, I went a bit more time higher than that. And thank you very much. And if
Online
I'm happy to
participant
answer
can
any
write
questions.
their questions in chat box. Yes, so there is a question. Sir, how can we reduce the staircase defect in the wire arc additive manufacturing?
That's again a bit very big challenging thing here. So uh, to reduce the staircase effect, most of them they make use of the adaptive type of element there. So like for example, the staircase effects are higher when we go when there is a curve like a shape, when there is a curve shape, or when there is a steep change in the shape. So that point is very higher. So what usually like we do, most of they do or is commonly used, so making the layer size smaller there. Okay, so making the layer height smaller there at that particular region. So that is possible when we can reduce the staircase effect. But There was a recent research from University of Manchester from there was Professor Charlie Wang at University of Manchester. He developed a real-time adjustment of that algorithm. So he developed some sort of like algorithm there. I will share that paper with you. I went to the particular paper. So he proposed some algorithms that can reduce the circus effect in real time.
And sir, as you mentioned in the slides also, the single layer, single track, multi-layer, and the multi-track single layer, the equations that we formed, how can we achieve those equations?
So we build that equation based on the data. We plotted, well, for example, we plotted the width and height, and we built a time series model. Like if you just Google out like how to build a time series model for predicting the width and height in real time, so we can plot that particular model. So we can it's a time series model with the support of we make use of MATLAB to plot that particular thing to build that equation.
And so there is a one another question from our colleague, sir. What are the postdoctoral opportunities over in the Ulster University?
Yes, there are postdoctoral opportunities. We actually go on here based on the project. So project is when we get any kind of a funding, then we release that particular thing. But keep an eye on it. Recently, we got another project on Northwest. We are building a Northwest Center for Advanced Manufacturing. So we sit here as this is a northwest region of an Ireland, Northern Ireland, and this particular is collaboration project between the Northern Ireland and Ireland. So there is almost a 10 million pound project for another 4 years. We are currently signing the agreement with that. Most probably, we're going to start its hiring on we're going to sign in October. So most probably, we're going to advertise the position in January. So that's again in additive manufacturing. I'm not saying only about Ulster, but that project will be having opportunities at Ulster University in Northern Ireland, Queen's University in Northern Ireland, and there will be the Atlantic Technological University in Northern in Ireland, and there is one other university at Trinity College Dublin. So there are four different universities. So four different, all are going to work on additive manufacturing. So you can have that particular opportunities looking up there. And if you just go on, maybe like for especially when it comes to UK, so there's a jobs.ac.uk page.
Sir,
So
could
on
you
that
please
page,
repeat it?
jobs j jobs.ac.uk.
Okay.
So that particular link, every this is a mandate for government that every position has to be advertised on that. So whether it could be like a 6 months or a year or 2 years or 4 years. So everything will come on that particular page. So keep eye on that. Like I'm not only of Ulster, but every university in the UK will advertise that position there. So keep eye on that, and definitely if I have anything coming in, and then I will let you guys know about that.
Thank you, sir. Thanks a lot. Any other participant have any query in the may write in the chat box? Okay, well, I think so. There is no other query. So thank you, sir, for giving the very deep insight in cyber physical system and digital twins in manufacturing. So it is our privilege to have you here, sir. So we look forward for further collaboration and opportunities. So once again, thank you, sir. Thanks a lot for giving this,
Yeah,
delivering the lecture, sir. Thank you, sir.
yeah. Thank you very much for you and the participants here for listening to these lectures there. And definitely, if anything comes up, if we can work in collaboration, we will go ahead with the some sort of work there. All right.
Sure, sir. Sure, sure. Definitely, sir.
Okay. Thank you.
Okay,
Thank
sir.
you very much.
Thank you,
Bye.
sir.
Bye. Bye.
Now we will have the short break for the lunch and we will reconnect the participant at 2 o'clock.